Hello everyone and good evening and welcome to this final lecture in the series on training neural networks. But before I begin, I'd like to thank my heroic PAs who are here recording this lecture at 9:04 in the night. Thank you very much guys. So I'd like to introduce these guys. Come on over, Hannah. So this is Hannah Muazzam, the lady with the sword. She is one of the three people who actually took all the effort. Stay here. I'd like to say hello. This is Wendy Velasquez. She's hero number 2, and Hari, hero number 3. These are the 3 people who I must thank and you must thank for this extra lecture that is being recorded late in the night. Thank you guys. So if you hear any mumbles in the background, it's them trying to figure out how to run the camera. So let me continue. I will not actually do a recap of everything that has been covered so far. I'll pick up where we left off at the end of last lecture, just mentioning that what we've done so far is that, what we've seen so far is that neural networks can be trained through gradient descent. But gradient descent by itself has convergence issues. It can be sped up using incremental updates like stochastic gradient descent and mini-batch descent. The convergence can be improved using smooth updates. The choice of the divergence that we use to define the loss actually affects the learned network and the results. Now let's get on with some of the other topics that we have mentioned earlier which actually affect how learning is performed. The first is this business of covariate shifts. When you train using mini-batch descent, we actually train over groups of data, each of which is a mini batch. We update the models over using groups of data, each of which forms a mini batch. The assumption here, is, as we saw in the last class, is that the statistics, the distribution of the instances within any mini batch roughly matches the overall distribution of the training data itself. In reality, this will not happen. In reality, so our assumption is that all of the mini batches, each of which is shown in a different color, sit more or less in the same region of the space, but in reality, here's what will happen. Each of the mini batches is going to be somewhat shifted with respect to the other mini batches, and also with respect to the overall distribution of the data. So each mini batch has a covariate shift with respect to the overall distribution of the data. And this is going to be true for every single layer, for every single neuron in the network. The inputs, the collection of inputs that every single neuron sees is going to have a distribution that has a covariate shift with respect to the inputs that it would have seen over the entire training data, had the entire training data be presented together. And in fact, this covariate shift can be quite large. So when all of the mini batches are shifted with respect to the overall distribution of the data, as you can imagine, this can affect the training, which assumes that all of these batches have distributions similar to the overall distribution of the data, badly. So what we would like to do is to move all these batches, mini batches, to a standard location such that this covariate shift is eliminated. And so to do so, we will move all the batches to have a mean of 0 and unit standard deviation, making sure firstly that the covariate shift between the mini batches has been cancelled out, and also any smear in the data has been accounted for. But simply cancelling out the mini covariate shift in this manner is not sufficient, because in this manner you lose the distinction between the individual neurons. So what we will finally do is to move all of these data, basically move every single mini batch to a standard location in the space, which is neuron specific. So here's what we will do. Every single mini batch of training that comes in is going to be shifted such that it now has 0 mean and unit standard deviation. And then the collection of data is going to be shifted to a neuron specific location in the space. This is what we will call batch normalization. So here's how batch normalization is performed. It's a covariate shift adjustment that happens after the weighted addition of inputs, right here, but before the application of the activation. It's done independently for each neuron to simplify computation, and the actual adjustment occurs over many batches. So consider a single neuron, it has a bunch of inputs. Here is the sequence of operations that normally happens. You compute a weighted affine combination of the inputs and then pass the affine combination through a activation function. In the batch normalized version, there's a small change. Once you compute the affine combination of inputs, this affine combination of inputs is normalized. You subtract the mean of the batch such that when you consider the ensemble of inputs in the mini batch, the mean of this ensemble is now 0, and you also divide by the standard deviation of the mini batch such that the standard deviation of the ensemble is now unity. And then having done this, now this Q is the normalized version which has been shifted such that over the mini batch the mean is 0 and the standard deviation is 1. That Q is now shifted through a second affine transform to a unit specific location. So the this U is transformed to Z act through this affine operation, which consists of a scaling and a shift. The scaling parameters gamma and beta are specific to every neuron. So here is the complete set of operations that are required. This first one computes the mean of these z values for the mini batch. The second term computes the standard deviation of these z values for the mini batch. So these two are used in the normalization of the z for any given training instance. In this manner, the mean is subtracted from the z and the mean shifted value is divided by the standard deviation. This plus epsilon is only used to make sure that the divisor doesn't become 0. And then finally, this normalized version U is scaled by gamma and shifted by beta. So here are all the terms. This mean is computed over a mini batch, so this B is the mini batch size. The standard deviation is also computed over the mini batch, so again this B is the mini batch size. Once the mean and standard deviation, the variance from which you get the standard deviation, once these terms are computed, you can use these to normalize the Z. And this is done by subtracting the mini batch mean and dividing by the mini batch standard deviation. And finally, the whole thing is shifted to a neuron specific position by a neuron specific affine transform. Now, here's a better picture for the whole operation. This is how I actually showed it earlier. For each neuron, first you compute this affine combination, then it goes through this batch normalization block, which has two stages. The first is the normalization U. The second is the affine shift of U to the standard neuron specific location. If you look closely, that looks like so. This U is the normalization step. The second step comprises a scaling of U by a term gamma and the addition of a constant beta. The resultant Z hat is sent through the activation F to get the output of the neuron. Again, this is only performed during training where we actually encounter mini batches. The batch normalization operation, which happens during training, influences the training procedure itself. Because we are actually computing terms, the mean and the standard deviation over many batches, the output of each neuron in response to any single input is actually influenced by what happens to the other inputs in the mini batch, and this is a problem. So to understand, let's look at what we do in conventional learning. In conventional learning, we attempt to compute the derivatives of the divergence for individual training instances with respect to the parameters. So we define our divergence for the mini batch, which is the average of the divergences between the output of the network for each input and the desired output of the network for that input. So when you compute the derivative of this divergence with respect to any parameter, this should have been a B, you actually compute the average of the derivatives of these divergences for each of the individual training instances with respect to that parameter. When you use batch normalization, this relationship changes. Here's what happens. Now the output y in respect to any input x is no longer a function of just that individual input. the output of the network in response to any input also depends on the mean and the standard deviation of the mini batch. And the mean and the standard deviation of the mini batch depend on the other inputs within that mini batch. As a result, this output y is no longer just an independent function of the current input, it's a function of the current input and all of the other inputs within the mini batch. And so computation of the derivative of this divergence between the output and the desired output is no longer a trivial task. You have to account for these dependencies across the mini batch. So, to represent this dependency, here's a better way of looking at the computation. So, let's say you have a bunch of different B different inputs in the mini batch. Then, for any single neuron, this picture doesn't represent a layer. It actually represents a single neuron. For any single neuron, the neuron has B inputs, one B affine inputs, one from each training instance in the mini batch, and computes for each of these instances the normalized and shifted version Z hat. So this actually ends up being a vector operation, but it's not a vector over the components of a single input. It's a vector over all of the inputs in the mini batch. Each neuron actually considers the collection of the affine combinations obtained from all of the inputs and computes the shifted versions for each of the inputs. The actual dependencies look like this. For any neuron, from all of the inputs for the mini batch, we will compute the global mean for the mini batch. Using these z's and the mean, we will compute the variance for the mini batch. And then the output in response to any single input is a function of the corresponding z and the mean and the standard deviation, both of which have been two terms, these two, have been computed from the entire mini batch. Now you can think of this as a complete vector operation and then use the standard rules of vector differentiation to compute the derivative of these u with respect to z. Again, this is the derivatives of the output of the batch normalization process with respect to the input of the batch normalization process, computed over the entire mini batch. But instead of using vector arithmetic like so, let's actually look at it in scalar terms just to get an idea of what is going on. So for any given input, the actual influence diagram looks like this. You have the affine combination that goes into the neuron. The affine combination is used to compute the mean of the mini batch and the standard deviation of the mini batch. Then this affine term z is then normalized to u, but the normalization utilizes the mean of the mini batch and the standard deviation of the mini batch. And this normalized u is subsequently fed to the activation function and thereafter to the rest of the network and generates the final output of the network from which you compute the divergence. So u influences the divergence. But then this divergence is also influenced by the rest of the inputs within the mini batch. So it's also influenced by the u terms that you compute for the rest of the mini batch. So when you compute the overall derivatives, when you compute the derivatives for backpropagation, here is what happens. Once again, here are all the operations for any given neuron. First, you compute the mean of the mini batch, then the standard deviation of the mini batch. Using these, you compute a normalized version u of the affine combination that goes in. And then from this u is further shifted to this new neuron-specific position through this transform, and then it's z hat that actually passes through the activation function. So when we compute our derivatives going backwards, as a first step, you compute a derivative of the divergence with respect to y for any given neuron. From those, we can just use the chain rule to compute the derivative with respect to z hat. All of this is very simple. We know exactly how to do this. Subsequently, observe that z hat is a function of u, gamma, and beta. So Gamma and beta are neuron-specific terms. They must also be estimated because these represent the neuron-specific position and the neuron-specific spread of the data. So to do so, you would need a derivative of the divergence to learn these terms using gradient descent. You would need the derivative of the divergence with respect to gamma, which is easy enough, because z hat, we already have the derivative of the divergence with respect to z hat. The derivative of the divergence with respect to gamma is simply going to be the derivative of the divergence with respect to z hat times u. So that's this term over here. Similarly, you can compute the derivative of the divergence with respect to beta as the derivative of the divergence with respect to z hat times the derivative of z hat with respect to beta. This last term is just 1 because z hat is simply a linear function of beta. So the derivative of the divergence with respect to beta is simply the derivative of the divergence with respect to z hat. This is easy. So we'll come all the way here. We have computed the derivative of the divergence with respect to this term, gamma and beta. Now let's take a step back. We can compute the derivative going backwards of the divergence with respect to u. And that is once again obtained from this formula over here. That's simply the derivative with respect to z hat times gamma. As you can see, z hat is simply gamma times u plus beta. So the derivative of the divergence with respect to u is going to be the derivative of the divergence with respect to z hat times the derivative of z hat with respect to u. And the second term is simply gamma. So this guy here now gives us the derivative of the divergence with respect to u. All of this is straightforward. Now comes the most complicated bit. Now you must compute the derivative of the divergence with respect to z for this particular input. Under normal circumstances, that would have simply been the derivative with respect to u times the derivative of u with respect to z. But the derivative of u with respect to z cannot be computed independently of the other inputs within the mini batch, and let's see why. Again, this is what we really want to compute, right? Now look at this. This is what really happens. The divergence is a function of u, but it's also a function of the mean of the mini batch and the variance of the mini batch. So, and the mean and the variance are in turn functions of z. So the derivative of the divergence with respect to z is going to be the derivative of the divergence with respect to u times the partial derivative of u with respect to z plus the derivative of the divergence with respect to mu times the partial derivative of mu with respect to z plus the derivative of the divergence with respect to sigma squared times the derivative of mu of sigma squared with respect to z. So let's draw the influence diagram to see how this works. Here are how things are, the influences are computed. Let me try drawing this. I have z. I hope you can see this. If this isn't red, maybe I should try a different color, blue. So here I have z, and z is influencing u, z is influencing mu b, and z is influencing sigma squared. All of these are influencing my final divergence. Now, in order to compute the derivative of the divergence with respect to z, I have to compute the derivatives down each of these three parts, which is what we got. This was the derivative of the divergence with respect to u, that's this guy, times du over dz, plus the derivative of the divergence with respect to mu, times du over dz, plus, can I go down here? Plus the derivative of the divergence with respect to sigma squared times the derivative of sigma squared with respect to z. This is, so when we have this plot, I have a reason for drawing the second version of this plot. There are three outgoing links from z to divergence, and you want to compute the derivatives contributions of each of these three outgoing links to the divergence. But when we do so, we want to make sure that we don't double count. The derivatives going backwards through each of these three links must only be counted once. That's just one. That's just one of the basic rules of differentiation. Okay. So now let's consider each of these three individual components. First, the central one. This is the derivative of the divergence with respect to sigma squared. This box here. This is the one that I've written at the bottom. Let's see how this works. Let me erase the rest of what's on this board. So I stay within the region that I can actually write. Now consider this. The standard deviation over here not only influences the current hue, the standard deviation influences every other hue in the batch. So the actual dependence diagram is what is shown out here. The standard deviation influences every hue in the mini batch, and each of these hues in turn influence the divergence. So basically, we will have the derivative of the divergence with respect to sigma squared is going to be the summation over all i's of the derivative of the divergence with respect to ui times the derivative of ui with respect to sigma squared. That's simply because of this dependence. Within the mini batch, the standard deviation of the mini batch affects the normalized term u for every every instance in the mini batch, and those in turn produce a bunch of outputs which all contribute to the divergence. So when we are going backwards, we are going to assume, remember from our figure, from the figure earlier, we are going to assume that we already have computed the derivative of the divergence with respect to u for every instance in the mini batch. So this term has been computed. What we are really interested in is in this term over here, and this, of course, this should be 1 over v averaging over the mini batch. Now, this, of course, is going to be another 1 over v doesn't come in. Anyway. So now let's look at this guy. You want dui over d sigma squared, and ui is going to be is just z minus mu over square root of sigma squared. Let's ignore the epsilon for now. So du over d sigma squared, this is z minus mu times sigma squared raised to half minus half. So this derivative is simply going to be minus half times z minus u times sigma squared raised to minus 3 over 2, which is over here. There's the second component to it. So this first derivative is just going to be this portion of it. I believe this guy is wrong. Okay. Now the second component is the derivative of, wait a minute. Divergence with respect to sigma squared. I'm not even sure what happened, right? There's a mess over here. That should have been du over d sigma squared.
They are combined.
Oh yeah. So
They are combined, right? Should be the.
there's a minus 3 over 2. I don't know how I actually missed this. Just keep it running for a bit of the progress. And then there's sigma squared over b. Let's correct this. Okay, anyway, let me continue. So I believe this the z minus mu b over here really shouldn't be here. And then you have the second term, which is the derivative of the sigma b squared over dzi. And here, of course, we have sigma squared is defined as sigma squared is 1 over b. Sigma squared is 1 over b summation I z minus mu whole squared. So when I take a derivative of sigma squared over dz, this is going to retain the 1 over b for any given I. That's only going to retain 2 times zi minus mu. So that's the second term is simply going to be the derivative of the standard deviation with respect to any z, simply 2 times zi minus mu. That accounts for this term in the middle, both of these terms in the middle, with one error in the slides. Then moving on, here's the second term. Now when you think of the derivative of the divergence with respect to the mean, when you consider the derivative of the divergence with respect to the mean has two paths influencing the divergence. The mean influences the current u. In fact, it influences all of the u's, and these u's in turn influence the divergence. But the mean also influences the variance. Changing the mean changes the variance. And the variance in turn also influences all of these u's, and thereby the divergence. We don't have to consider specifically the derivative, the dependence of the variance of the various u's and the variance, but when it comes to just considering the derivative of the divergence with respect to the mean, we can just see that here is what we have. We've got this dependency. The mean influences each of the u's. The mean influences each of the u's. The mean also influences the variance. All of these terms in turn influence the divergence. So if you want the derivative of the divergence with respect to the mean, this is going to be the sum over all i's, the derivative of the divergence with respect to ui, which as we saw earlier has already been computed, times the derivative of the ui's with respect to the mean, plus the derivative of the divergence with respect to sigma squared times the derivative of the divergence of sigma squared with respect to the mean. Now, let's consider this second term first. The derivative of sigma squared with respect to the mean. Sigma squared equals 1 over b summation I zi minus mu squared. So if I take the derivative d mu, that's going to be minus 2 over b times summation I zi minus mu. And this term over here, you can see trivially enough, this is going to be 0. So the second term over here will simply go to 0. That's because if you sum, this mean is simply the average of the z's. So if you see this guy over here, this is going to be summation I z minus summation I mu, which is summation I z minus summation I z, which is 0, right? So now let's consider the first term, this guy. This guy is going to be just this yeah. Why am I getting confused here? Let me see. Z with respect to mu, right? No. I'm totally confused over here. U with respect to mu. Oh yes. So let's consider this for this first term over here. This first term is simply going to be the derivative over I d divergence over ui times, again keep in mind that ui equals z minus mu over square root of sigma squared, implies du over d mu is going to be minus 1 over square root of sigma squared. So this is going to be 1 minus 1 over square root of sigma squared plus epsilon if you want to be careful. So that gives us this first term. So you have two terms over here when you compute the derivative of the divergence with respect to mu, and of which one of the two terms becomes 0. So the overall divergence simply ends up being this term. The derivative of the overall derivative of the divergence with respect to mu simply ends up being this one term. That leaves us with the last term, which is, and then the derivative of the mean with respect to z. The derivative of the mean with respect to z is again very straightforward. The mean, mu, is simply 1 over b summation I zi. So the derivative of the mean with respect to any given zi is simply going to be 1 over b. That's very simple. That's simple. So we've considered this term, all the component terms here and all the component terms here. Now let's go to the first term. The first term is again the derivative of the divergence with respect to u times the derivative of u with respect to z. But u is simply z minus mu over b over the standard deviation. So the derivative of u with respect to z is simply going to be 1 over the standard deviation, 1 over square root of sigma squared. So in effect, we have computed every one of the terms required to compute this derivative of the divergence with respect to z. And so once you do so, here is the overall derivative that we get of the divergence with respect to z. Derivative of the divergence with respect to u times the derivative of u with respect to z times the derivative of the divergence with respect to sigma squared, which is given up there, times the derivative of sigma squared with respect to z, plus the derivative of the divergence with respect to mu, which is also given up there, times the derivative of mu with respect to z. So the entire thing the entire thing can now be computed, the derivative of the divergence with respect to this z term. And once you do that, from here, the rest of backprop can be continued onto the inverse as before. So this may sound a little bit convoluted, and maybe I made a little bit of a heavy weather of it, but if you actually go over it, it's very straightforward. So we know how to propagate gradients backwards when we perform batch normalization, but during training, we were training over mini batches. Each mini batch had a covariate shift, which we characterized by the mean and the standard deviation of the mini batch, which we cancelled out. During inference, we don't have mini batches. We have only one instance. So what are the means and variance standard deviations we will cancel out? Since the individual instances don't really have means and standard deviations, what we will do is to compute the average of the means of the mini batches over the entire training data. We will compute the average of the variances of all of the mini batches over the entire training data. Specifically, we will compute the unbiased estimate. So if you simply divide by the sum the means of all of the mini batches and divide by the number of mini batches, that gives you the average mean over all mini batches. This simple operation is not sufficient for the variance. You also have to multiply by b over b minus 1 to obtain an unbiased estimator. I won't go into the details of what it means to have an unbiased estimator. You can take this on faith. But the essential fact is that we are computing the average of the means of the mini batches in the training data and the average of the standard deviations of the mini batches in the training data. And this is what we will apply. These are the guys that we will apply to our test instances during inference time. Now, batch normalization doesn't have to be applied to every neuron or to every layer. You can apply to only some layers in the network, or even to some neurons in the network. You may apply it either to the affine combination at the input of the network or to the output of the activations. These are various variants that have been tried, and there's anecdotal evidence that batch normalization, when done properly, actually eliminates the need of dropout, which we will see in a few minutes, as a regularizer. To get the maximum benefit from batch normalization, however, learning rates must be increased and learning decay can be faster. This handles the fact that since data are being normalized, you have less of a variation in the data to account for. Also, for batch normalization to work properly, the mini batches themselves must be properly organized, which means that better randomization of training order can be critical to the application of batch normalization. Here are some results on ImageNet that Yoff and Regularization reported in 2015 on how much batch normalization actually influences training. And you have various curves. The two curves to the extreme left show result or show test set accuracy as a function of the number of iterations, I believe. And you can see batch normalization, different variants of batch normalization actually train models much faster than simple baseline gradient descent or its variance. So the story so far, gradient descent can be sped up by incremental updates, and this convergence can be improved using smooth updates. The choice of divergence affects both the learned network and results, and the covariate shift between training and test data may cause problems which can be handled by batch normalization. Now, all of this is fine. We've gone over a lot of what training really does and various ways of trying to control convergence and so on. But in all of this, I've hidden a fact. Many of the illustrations I had were plain wrong. How's that so? Consider this. This is an illustration we've seen several times. This figure to the left shows a function that we would like to learn. The red lines show the specific input-output pairs from which we want to learn the function. That's because we don't have a complete specification of the function, only the input-output pairs. The figure to the right shows only these input-output pairs, and that is what these guys are what we will be using to actually train the network which models this entire function. But in reality, and so here's how we'll train it. At any point, our current network is going to give us some estimate of the function, but not of the function. It's going to give us some current output in response to these inputs. There will be some error between the current output and the output that we really require. We define a loss which quantifies the error between the current and desired outputs. We minimize this loss. But here's what really happens. You have this continuous input space, and you have a small number of input samples over the input space. In fact, the number of samples is being discrete. The total volume occupied by your training data is identically equal to 0. Your training data occupies no volume at all over the data space. So which means that so long as you match the input-output relationships over here, you have no control over what the function that is actually modeled in the rest of the space is. So while you might be wanting to generate this dotted blue line as your function, you may just end up with the red curve as your function. So, and first, to understand the extent of under-specification, even this figure is highly exaggerated. To see how exaggerated it is, let's consider this simple example where we are trying to learn over a function over a 100-dimensional input where each component is binary and can only take two values, 0 and 1, which means that our data live on the corners of a unit hypercube. There are 2 raised to 100 possible corners to this hypercube, which is about 10 raised to 30 values. And so the input data can take only one of 10 raised to 30 values. But 10 raised to 30 is a tremendously high number. So now suppose I give you 10 raised to 15 training instances, which is several trillion training instances. 10 raised to 15 training instances can at best cover 1 over 10 raised to 15 of the entire set of values that the input can take. Basically, even after getting trillions of training instances, you are covering none of the input space at all. In fact, if you dial the dimensions back in a logarithmic sense, this is the equivalent of giving one single point for each component of your, each dimension of your input space and saying, find me this function. Now, as you can see, this is clearly absurd. So you can't find an entire function using just one point. This means you need additional constraints that somehow constrain how the network fills in these intermediate values in the space acceptably. This relates to generalization. Now, to understand this, consider the simple binary classifier. You have a network that must learn a relationship between the input and the output. And the training data points are one-dimensional in this case, and you get these two sets of training data points. The red points are one class, the blue points are the other class. Now, the desired output in this kind of a case, as we've seen earlier, is some kind of a smooth function that is shown by the blue curve. But since the network itself is a universal approximator and can capture pretty much any function, if it's unconstrained, it can simply learn to model each of the training instances perfectly. So it could end up learning this purple curve as opposed to the continuous blue curve. So the unconstrained model could end up learning this function instead, which clearly is not what you would want in many situations. Now, why does this happen? This happens because an unconstrained network has the ability to have these really sharp changes in value. That's because the individual perceptrons in the network are capable of very sharp changes if they are unconstrained. To get an idea, consider this simple situation where every perceptron, the activation for every perceptron is a sigmoid. I'm just using a sigmoid for illustration, but this holds regardless of what activation function you use. So, if your perceptron's activation is a sigmoid, now all of these are valid sigmoids. Something that's this deep, something that's this shallow, all of these, they're all crossed at the same point. All of these are valid sigmoids. You can make the sigmoid arbitrarily sharp simply by changing the weight of the input that is applied in the that is used in the affine combination that is exponentiated within the sigmoid. So over here, when the weight is 0.5, you get this blue curve. When the weight is 5, you get this steep red curve. If the weight was 500, the output of the sigmoid is going to look almost exactly like a step function. What this means is that every one of these neurons is individually capable of modeling an extremely steep step function, as a result of which the overall network can actually have very steep outputs and end up giving you this kind of function as opposed to what you really want, which is the smoother function, which is this one. So one way to make sure that the network doesn't actually learn the ugly red function and learns the blue function instead is to somehow make sure that none of the individual neurons in the network are capable of representing such steep functions. And that constraint can be imposed by imposing constraints on the weights. So for each of the individual neurons, if the weights are unconstrained, the function itself can be arbitrarily steep. So if you impose the additional constraint that you want the weights to be small, then you are forcing the function to be smooth as opposed to and very slowly as opposed to taking on that very steep shape. So how would you impose this constraint that you actually want, or the requirement that you would like the weights of the within the network to also be small? That we would do by modifying the objective function. Now, your standard loss function is computed like so. On each training input, you compute a divergence, which is a function of all of the parameters of the network. The loss is the average of this divergence, and you actually minimize this loss with respect to all of the parameters in the network. Instead of doing this, we will now add a second term, which is simply some weight times the square length of the weights vector. Now by adding the second term over here, which is the square alpha norm of the weights vector, to the loss, this ensures that when you actually minimize the loss, you're also minimizing the weights. This term, the term lambda, controls how important you believe the minimization of weights or reduction of the magnitude of the weights to be. It's a regularization parameter which can be set according to your belief on the importance of having a smooth function and how much you would like to constrain the weights. The modified loss, the regularization parameter typically can be adjusted either heuristically or through some tests on some held out data. The modified loss results in modified derivatives, but the modification of the derivative itself is fairly trivial. All that happens is that the standard derivative is now augmented with an additional term, which is simply exactly equal to lambda times the current set of weights, which makes the gradient descent rule itself very simple to implement, and the computation of the derivatives too, very simple to implement. So if you were to write pseudocode for the whole entire operation with regularization, this is the incremental update mini batch version where we have now included an additional component that accounts for the regularization of the weights, which is to say we also try to minimize the lengths of the weight vectors themselves, and that simply takes this form where the gradients are now added. The current weight vector, the scaled current weight vector, is now simply summed to the current gradients. There's another way of trying to impose smoothness on the network output through network structure. And this takes advantage of the fact that multi-layer perceptrons naturally impose constraints. Multi-layer perceptrons, as we know, are universal approximators. If you arbitrarily increase the size, it can give you arbitrarily wiggly functions. The function itself, however, will remain ill-defined in the majority of the space. Yet you have this one feature that for a given number of parameters, deeper networks impose more smoothness than shallow ones. Remember, if I fix the number of parameters, I can either arrange these in a shallow but wide network or a deep but narrow networks. When I have a deep but narrow network, each layer works on the output of the previous layer. And if the previous layer has already smoothed the function, then each layer is going to be working and smoothing an already smooth function. And this has a consequence, and that I will illustrate empirically. Here's an example. In this example, there's a two-dimensional example. And one, I'm trying to learn this decision boundary, which is the arrow, and the other, I'm trying to learn this one, where I want a 1 within the white regions and a 0 in the black regions. We have sampled this training data, and we have 1,000 training points, which, as we saw, is orders of magnitude more than you would usually get in a real problem where you typically get less than, just a fraction over one data point per effective dimension, right? So, and we've tossed in all of the training tricks known to mankind, and with fairly large networks with 660 neurons, here are the decision boundaries that you actually end up learning, and they aren't what you want at all. On the other hand, if I begin arranging these, so in this case I have one hidden layer. Now if I begin arranging the same neurons with greater depth, here's what happens. So here are two examples. This is this shape which looks like a nut. The other has a decision boundary that actually is in the shape of a bear. Now in each case I have 660 neurons. Here I'm arranging them in 3 layers of 220 hidden neurons. There are 3 layers of 220. There are 4 layers of 115, 6 layers of 110, and 11 layers of 60. And as you can see that as I increase the depth and narrow the network, the function does a better and better job of modeling the decision boundary that I actually want. Sort of illustrating the fact that if you rearrange the same number of neurons, or more generally the same number of parameters, into a deeper but narrower network, you get a greater regularization effect, which is more likely to give you the kind of smooth functions that you actually want. Again, the assumption here is that you really desire the smooth function. If that is not what you desire, then of course all bets are off. Now, the nice thing is the rearrangement of neurons in this simple manner into deep but narrow networks gives you this kind of smoothing and regularization, which provides the kind of flexibility that's often not available with other pattern recognition models. Now, all of these upper examples have been obtained using, I think, about 1,000 training instances. There's a third way of doing a better job of learning, which is to simply provide more training instances. So here, if I give you 10,000 training instances, it actually learns the boundary that you want. But this situation is something that you're rarely, if at all, ever going to see in real life. There have been other techniques that have been proposed to improve the smoothness of the learn function, like Mellon regularization of network activations, adding noise to the input to regularize it. But possibly the most influential method has been this technique called dropout. And we'll get to that. But first, the story so far. We've seen that gradient descent can be sped up by incremental updates, and convergence can be improved by using smoothed updates. The choice of divergence affects both the learned network and the results. Covariate shifts between training and test may cause problems and can be handled by batch normalization. Data under-specification can result in overfitted networks and must be handled by regularization and more constrained, generally deeper architectures. So let's go on to Dropout, which has been very influential in the literature. But first, a brief detour into this concept called bagging that anybody who has taken any course in machine learning is probably already familiar with. This was a technique proposed several decades ago by Leo Breiman, where the idea is to exploit the fact that if you train a diverse collection of different classifiers and take a vote over these classifiers, you can do a better job than if you simply train one classifier. So here you use the sample training data. You would sample the training data and train several different classifiers. You generate several different samples and have several different classifiers. And then when you get the test instance is going to go through each of these classifiers, each of which is going to provide a potentially different prediction. And the final classifier is going to combine all of these predictions through a voting scheme to give you the final output. And empirically and even theoretically, this can be shown to significantly improve over training only a single classifier from the combined data. So let's return to our problem. Here, in our standard network, we have a multi-layer perceptron where we have several layers of networks, all of which process the input and finally provide the output. And this technique called dropout, during training for each input at each iteration, we would turn off each of the neurons with a probability 1 minus alpha. So this would include the inputs as well. So for example, for one training instance, if you look at this guy, compare it to this one, you might have one set of training instances being dropped out. Now in reality what happens is that we don't physically delete the neurons from the network, we just force their outputs. The outputs of these neurons to 0. So in practice, you'll be flipping a coin, be running a Bernoulli random number generator, and every neuron is going to be set to 0 with a probability probability 1 minus alpha, and the value is going to be retained with a probability alpha. Each input this is done separately for each input, which means that each input is effectively going to see a different network because different sets of neurons are switched off for each input. So the pattern of drop nodes would actually change for each input, and not only for each input. If you're making multiple passes through the training data, then each time an input encounters the network, it will see a different version of the network because a different set of neurons have been dropped out. So the pattern of dropped out neural nodes and the effective network seen by each neuron is going to be different in each seen by each neuron. Each input is going to be different. Not only that, each input is going to see a different network in each pass through the training data. Now, when you do this, if you're computing gradients using backpropagation, the only portion of the network that remains is the network that's composed of the set of neurons that have not been switched off, the ones that are on. And so backpropagation itself must carefully only utilize the portions of the network that actually remain for any given input. Now, how many such networks can we actually compose? If a network has n neurons, then there are 2 to the n possible subnetworks that you can compose by switching on by switching on or off neurons. So what dropout does is so effectively the theory says that dropout actually views each of these 2 to the n possible networks, which are formed by dropping different subsets of neurons off as 2 to the n separate classifiers, and the final classification is actually performed as a vote over all of these 2 to the n possible networks. And so, but instead of explicitly training all 2 to the n possible networks, you randomly sample from these 2 to the n possible networks by randomly dropping individual neurons for each training instance during each training pass. But the actual effect is the same as bang. So there's another way of looking at it. Dropout forces neurons to learn rich and redundant features. Now, if you don't actually perform dropout, and if you have a network with a layer such as this, there's absolutely nothing in the training process that to ensure that the network simply doesn't learn to pass the output of this neuron to pass this input directly to the next layer, such that which is basically a trivial translation of the input to the next layer, ignoring all of these cross connections. Effectively, your network loses a layer because at some point one layer simply clones the previous layer, and this can happen. But if you are dropping things out, then every time you switched off a neuron, its input, its information is no longer being passed to the next layer. So dropout sort of forces the network to ensure that the next layer actually considers all of the inputs from the previous layer to compute its current output. So dropout effectively forces the network weights to have denser patterns. It forces it to learn dense patterns with redundancy. So here's how you would actually implement dropout during the forward pass. In each layer, you would run compute a Bernoulli random variable that has a probability of alpha of being on, and use that to compute a mask for the layer, which tells you which neurons are on and which neurons are off. And if any neuron is off, you're going to set the corresponding output off. You would retain this mask. And then during the backward pass, we have to consider the mask that was used in the forward pass, and we only propagate the gradients backwards through the neurons that were not switched off as marked by the mask. Now, what each neuron actually computes has the following activation. It's the actual activation of the neuron, multiplied by this Bernoulli variable d, which takes a value 1 with a probability alpha. So the expected output of the neuron over any ensemble of inputs is going to be simply alpha times the output of the neuron, because some alpha fraction of the time the neuron is switched on, and 1 minus alpha times it's switched off. Now during test time, if you're actually performing bagging, you'll be computing the expected output over the entire ensemble of inputs. So during test time, what you really want to do is you want to compute over the expectation over all 2 raised to n possible networks of the function of x, right? Where x is the input, or more explicitly, you would be computing the expectation over all 2 raised to possible 2 raised to n possible networks of the function of the outputs of the individual neurons in X. So this function f itself represents the network. The GIs represent the individual neurons in the network. Now this is what you would like to compute. On the other hand, actually going over all 2 raised to n possible network is not going to be feasible. So what we will do instead is a very simple approximation. We're going to assume that the expected value of the function of G1, G2, G3, and so on is approximately equal to the function of the expected value of G1, the expected value of G2, and so on. So this is an approximation. You're approximating the expectation of a function by the function of an expectation. But once you make this approximation, then the computation becomes tractable and trivial. So what we will do during test time is to explicitly compute this term. Now, what is the expected value of the output of any network? The expected value of the output of any neuron? The expected value of the output of any neuron is simply going to be the expected value that is going to be switched on times the actual value of the neuron itself. And this is simply the fraction alpha that is used during the training of the network times sigma. So which means that we are going to be computing the output of the network as f times alpha G1 comma alpha G2 and so on. Now this is an approximation. It's not the actual bagging output that you'd want, but it makes things tractable. And here's how you can implement it. During training, you can during the inference time, the output of any neuron can simply be computed as alpha times sigma. But to implement it, you can actually make things even simpler. Now consider this: the output of any neuron is alpha times the output of the activation. So there's an alpha multiplier that applies to all of these neurons. This alpha multiplier, instead of applying to the outputs of these neurons, can be directly applied instead to the weights of the edges going on to the neurons. Which means all you have to do is scale the weights up or down by a factor alpha, and use the scaled weights directly in the network to compute its outputs, and everything will work just fine. Or alternately, instead of scaling the weights or scaling the outputs of the neuron during inference, during training you can scale the outputs of the neurons by the inverse of alpha after applying dropout, and then train your network, and then during inference time just use sigma itself, and nothing really changes. So both of these are valid implementations. So here is the inference loop for dropout. During test time, you're going to, if you have a dropout layer, so during training time, you would actually be dividing by alpha. There's something wrong with the slide. And you'd be using the divided by alpha version along with the mask during the forward pass during training, and nothing else changes. So here are some typical results for dropout from Nitish Srivastava et al. In 2013. Test errors of different architectures of MNest with and without dropout. And they show the influence of regularizing the dropout, and they show that across different runs, different architectures, you get a very large improvement in classification error if you actually regularize using dropout. There are various variations on dropout. So for recurrent neural networks, you have something called zero out, which randomly chooses where randomly chosen units remain unchanged across a time transition. We'll encounter these later in the course. Instead of switching off neurons, you can just switch off individual connections. This gives you something called drop connect. And then there are other variants like shakeout, whiteout, any number of variations from the basic idea. But the basic idea remains the same, that you can randomly switch off components of the network and effectively get a bagged ensemble output over many networks from a single network in this process. And that should give you better prediction during test time than simply employing a simple, straightforward network. So the story so far: gradient descent can be sped up by incremental updates. Convergence can be improved using smooth updates. The choice of divergence affects the learned network and the results. Covariate shift can cause problems and must be handled by batch normalization. Data under-specification can result in overfitted models and must be handled by regularization or more constrained network architectures. And dropout is a stochastic data or model erasure method that sometimes forces the network to learn more robust models. Now I'm using the word sometimes because it doesn't always give you benefits, and there are situations where you really mustn't be using it. There are also interactions of dropouts with other optimization methods like batch normalization. Now some of this are empirical lessons and a little bit of art that you must learn through practice. There are other heuristics that we will employ. Continued training can result in overfitting to the data. So a standard approach is to track the performance, the classification performance of the network on a held out validation set, and apply one of several early stopping criteria to terminate training when the performance of the validation set either plateaus or begins to degrade. Another issue that happens is very often the way training happens, some of the neurons in the network will end up taking too much of the responsibility for the output. And so these neurons will have both the outputs of these neurons and the derivatives of the parameters of these neurons will have very large, both the outputs of the neurons and the parameters of these neurons will have very large derivatives with respect. The derivative of the output with respect to these terms can be very large. In other words, these terms can have an unduly great influence on the output of the network. So in these cases, you will find that the derivative of the loss with respect to the parameter or even the output of the neuron can be very high. So in order to reduce the influence of these neurons and to control for the instability that can occur from such high derivatives, there's a common technique which is gradient clipping, which sets a ceiling on the derivative value. If the derivative exceeds some value theta, which is typically about 5, then you just set the value to theta and don't let it go higher than that value. There are other heuristics like data augmentation. Very often your training data will be small, so you can extend it by distorting examples from your training data in a variety of ways. For example, if these are images, you could rotate them around, you can distort them in minor ways, stretching, adding noise, and so on. And you know that this distortion hasn't actually changed the label of the training data. So you get an augmented training data that you can use to train your network. There are other tricks like normalizing the input, which is to apply covariance shifts to the entire training data to make it zero mean unit variance, which is equivalent of batch norm on the input, or various initialization techniques. Typically, the networks are initialized randomly, but but it's important to make sure that all the parameters are different when you initialize the network, because neurons with identical connections that are identically initialized will not diverge. Several other tricks. So training these networks actually ends up being, although there's a lot that we've gone into in terms of concepts and theory, by the time you get to the end, it ends up being a bit of an art that requires practice. So here's how you set up the problem. You start off with training some training data, use appropriate representations for inputs and outputs, choose a target network architecture. If you have more neurons, you'll need more data. Deep networks are better than shallow networks, but these come with their own problems, which we'll see later. You use the appropriate divergence function and the appropriate regularization. Choose your heuristics like batch normalization, dropout. Choose the appropriate optimization algorithm. Typically, we just use Adam because, as we saw in the last class, Adam has this nice habit of accounting for both the expected value of the divergence and the root mean square value of the divergence, which ensures that of the gradients, which ensures that the gradients don't swing around wildly. And once all of these are set out, you can perform a grid search for hyperparameters on held data, typically learning rate, regularization, whatever, and then just train. So in closing, what we've done over the past several lectures is to outline the process of training neural networks with some history, a variety of algorithms. We've talked about gradient descent-based techniques. We've talked about regularization for generalization, algorithms for convergence, and heuristics. But in the end, practice makes perfect. The more you actually work on training networks of different kinds, the more you will get a handle of how these things work and what is the best way of training these networks and how to actually make them work for you. So I'll stop right here, and please make sure to go over not just this lecture but all associated material on the various topics that we mentioned, some of which will be on the course website, others I recommend that you dig up on your own from the web. Good luck and thank you.